Welcome to this video on dynamic optimization. In this video we will talk about how to numerically solve general dynamic optimization problems. In order to do this, you will also need to learn a bit of simple function approximation. In particular, we will talk about linear interpolation. I should make you aware that this is a hard subject, but with the tools that we cover in this video, you will be able to solve a broad range of economic models. But let us get into it. So I'm importing mostly standard stuff, and then this interpolate sub-package from SciPy as well. But first, let's talk about interpolation. So what I think of when I say interpolation is that I have a situation where I have a sorted vector of known points, a so-called grid vector. That's just some points, and then I know a function at these points. So I know the function values at the points that are in G. And then I come with a new point x that's not in G, but where I want to know the value of the function, but I want to know it without being required to evaluate the function. One way to do that is to use linear interpolation. And that's rather simple. The idea just is that you find an index into the grid vector such that the x it's larger than or equal to the I value in the grid, but smaller than the next value, the I plus 1 value in the grid. Once you know this I, then you take the function value at the point to the left, you find the slope that we have in the of the function. So this is a linear approximation of the slope in the function. And then you take how much to the left of the point I, so how long away are we. So this is similar to a Taylor approximation. And then we calculate the function value based on that. If we have the case that we have an x that's below our grid, or at least below the second grid point, then we will use the first the I0 as sort of where to calculate our linear approximation. So this is the same formula as up here, just with I equal to 0. Similarly, if we are above the next to last value, then we will use this as a basis, and we will extrapolate out based on that. Okay, so let's see how we could implement this. So this is a function taking the known points, the values at these points, and then this new point x to be evaluated or to be interpolated. I first check that I have the same number of grid points and known points, and then I find out how long are my vector of points. If I extrapolate below, then I set my I equal to 0, otherwise I set it equal to n minus 1. And then I simply do the search such that I find the I in the way I specified above, where I'm certain that it is equal to, larger than or equal to the GI value, and at the same time smaller than the I plus 1 value. Then I do simply the interpolation step. I find the slope and I apply it in the way stated in the formula above. So that's rather simple to implement. Let's see it in practice. Here I use some function, and I create some grid vector, and I evaluate my function at this grid. Then I also create a fine grid. I have 500 points here, so that's a very, very fine grid, and I sort of call this the true functions values. Then I make a simple test where I loop through some new points, this big X, and then I evaluate both the true value of the function there, and I do my interpolation function. And then I print out what was the X value, what is the true value, and what's my interpolated value. And then I make a plot of this. So if we evaluate this, then we can see that for my various X values, the true values and the interpolated values are sort of close. They're at least sort of similar. In the similar direction. And you also see that if you sort of do the plot, then these squares, that's the interpolated values, the circles that are the known points, and then I sort of have the true function as the curve. And you can see that the squares are almost on the curve. If you look closely, you can sort of see that they are sort of on linear segments between the known points. So if we are very close to a point, then it's a good approximation, but if we are further away, then it's generally a worse approximation. So that's basically how linear interpolation works. You get a good approximation of the function value without actually evaluating the function. Instead of writing our own interpolate function, we can also use a function from SciPy. So this is the regular grid interpolator, where you specify a list with the grid in it, and then you specify the known values, and you specify this bounds error equal false and filled value equal none in order to allow for extrapolation. And then once you have set up this interpolation function, then you can just apply it to the vector of points, and we will get exactly the same plot as below. So this is exactly the same. Okay, so let's also consider this in a slightly different way. So instead of plotting the interpolated values as squares here, I will now think about what I find sort of an interpolated function where I linearly approximate between the points that I have. And then it looks like this. And then I want you to pause the video and try to increase the number of known points and see what happens. Okay, let me try to do it as well. So I could say that instead of 6 points, we could have 8 points. And you sort of see that the interpolated function gets closer. And I could sort of go up to 12 points. Oh, now it gets really, really good. And I could go up to 100 points. And so you see that it gets really good, but then it's bad out here. So why is it really good and then bad in the ends? That's because that my known points here, they are still between -5 and 10. While my grid that I specified, that's between, I think, -6 and 12. And therefore there will be extrapolation out here. And that's generally a bad thing. Extrapolation is much bigger errors than in interpolation. So that's sort of what you should take away. If linear interpolation can be work really well when the function is smooth and we have a lot of known points, but extrapolation can be bad. Even though we don't need it here, it should also be stated that you can actually just do the same thing in multiple dimensions. So if you have a 3-dimensional function, then you will just specify 3 grids and it will work in a similar way. Okay, so now we know what we need to know about interpolation. So let's think about a dynamic optimization problem. And what I mean by dynamic is that there's a series of optimization problems that sort of solve dynamically over time. So we always think about this backwards. So we consider households that live in 2 periods, and we start in the second period, the final period in the problem. And we see that the household gets utility from consuming and leaving a bequest. So this is the utility of consuming, and this is the utility of the bequest. And sort of you have some cash in hand, M2, you consume something, C2, and then you have end of period assets, A2, and they have to be non-negative. And the parameters are defined in more detail down here. Okay, so what we have is that we have this value function, the v2 of M2. Now there's a 2 missing there, which measures the household's value of having this cash on hand at the beginning of period 2. So that's a function we will like to know at some point. But for now, just define the utility function, the bequest function, and the last value function here. So that's just as I write it in the math. Then in the first period, the households get utility for consumption, but they also take into account that they will live in the next period where they receive a stochastic income. So now they will start out with some cash on hand, M1. Then they will consume something, C1. They will get utility from that. That will leave them with some end of period assets. That will determine their cash on hand in the next period, where they will have 1 plus a return rate times the end of period assets plus some income. And now the special thing is that this income is stochastic. So with one probability P, it's 1 plus delta, and with probability 1 minus P is 1 minus delta. This implies that the problem is dynamic. You need to first decide what you do in the first period, and then the stochastic income will be realized, and you will decide what you do in the next period. We still have the requirement that you cannot borrow, that asset has to be non-negative. Okay, so now we want to solve this whole problem. We can first sort of define what is this value function here actually doing here. So this is just a way to implement what I had above. We say that we don't know what the expected value are to begin with, so that's the expected part of this. So we say, okay, we use that our p here can either be our actual p, or it can be our 1 plus part of delta, and it can, or it can be the opposite. And then I say for a given consumption choice, for a given cash in hand, for a given parameters, and a given interpolation function for the next period value, then I can evaluate my functions. I can say this is the end of period assets, this is my cash in hand in the next period. Then I can evaluate my interpolation of the next period value, and I can increment my overall value from the next period by taking the interpolated value and multiplying it with the probability that this happens. So this is just the way you implement this expectation up here. And then in total, the utility is the utility of consumption, and then this discounted expected utility. Okay, so let's define this. So if we sort of have an overview here now, our problem is we want to find the functions v2, v1, and we want to find the consumption functions c2 and c1, which determines what you want to do. And we want to do this on some grid for m. So note this is different from when we usually solve optimization problems that are static. Then we will find sort of a solution to the problem, the maximizing value, or at least a set of maximizing values. But here we are interested in saying, given that this is your input, what will the optimal decision be? And so we need to solve the household problem. So I simply set up the parameters for doing that. I set up the preferences, I set the return on income, and I set a grid for which m values do I want to do it for. The number of grid points, the minimum value, and the maximum value. So let us define that. Then to solve the last period, I think that I now know my parameters. I set up my grid. I define some space for where I want to put my my functions here, and then I solve it by looping through my grid. So I look at each point in the grid. I say my objective will be the negative of the value, because I will be using an optimizer, which is actually a minimizer. I will guess that I will consume half of my cash in hand, and this will be coming from using the minimize function in SciPy, and I will use the this BFGS, which allows for bounds. So I will specify bounds as between close to 0 and my full cash in hand. If I go above this, then I will be borrowing, and that's not allowed. Finally, I will be saving what the value is by taking the negative of this result, and I will be saving what the consumption choice is by taking the result. Okay, so I can do that. Then I can actually apply the function, and I can plot how it looks. So now here we have a nice consumption function, and we have the associated value function. We can sort of think about why is there a kink here, and that's basically because to begin with we will consume all our cash in hand, but at some point we will begin to split our assets in between consumption and bequests. So that's why sort of there will be sort of a kink at a specific point here. Okay, so now we have solved the second period. How do we proceed? In order to solve the first period, we will need this about interpolation. So we will create an interpolator based on the grid that we have for the second period and the value for the second period. So we define that. And then we can define a function that's very similar to the other one to solve the first period. Now, sort of this is the same. We allocate in the same way. We loop over the grid in the same way. Now our objective is the V. So that's the general formulation of the problem instead of the last period. And we simply put in the cash in hand and this interpolator function. We guess again on consuming half, and we do it exactly in the same way. So we can do that, and then we can solve it, and we get out our consumption function and value function again. So, but now we have them in the first period. So to wrap up here in terms of solving, then we have now we can sort of collect everything we have been doing in one function, where we first solve the second period, then we construct an interpolator, and then we solve the first period. Okay, so that's actually nice. One thing we can use that for is that we can now sort of try to see, let's see, we vary the size of delta from a low value, a mid value, and a high value. So this was the spread in income. When delta is high, then sort of the difference between the high and the low income is bigger. And each time I set the delta, I solve my my problem, which to go through all these steps up here, and then I reset my delta, and I will be plotting how the consumption function looks like. That takes a bit of time, but once it's done, we can sort of see that the consumption function is falling in delta. So if delta gets larger, that is the income spread gets larger, then the households reduce their, I think I've written value function here, but this should be consumption function. Okay, now I need to resolve it again. Let's just ensure that I actually plotted the right thing. Yeah, I plotted the consumption function up here, so that's fine. So we will have that the consumption function falls when risk increases, and for example, that could be what happens in a recession, and that's called precautionary saving. And that's basically something that's very hard to work with analytically, but you can see that it's rather straightforward to do numerically. This is a good time to pause the video and ensure that you understand what we have done so far, and try to run some of this stuff yourself. One task you can try to work with is what happens to the consumption function if beta increases. So here I have a high beta, and I increase it with some part, and then you can see what happens with the consumption function. People get more patient, so that should be another reason for why consumption should decrease. So try to show that here. Okay, now we have solved a 2-period problem, and for many sort of theoretical consideration, that can be enough for doing a lot of interesting dynamics. But we can actually easily add more periods. So we can think about the problem in more general terms as just being something that goes on from period t to period t plus 1. There's a small mistake here, so that should be a t. So we now sort of just have our value function of the cash in hand in period t, and then we take the expectation with respect to t plus 1, and in this way we now have sort of a whole series of problems that we are solving. And we can sort of set this up in the following way, where we say now we have a function for solving many periods. We now allocate a solution simple namespace where we will save what the grids and the value function and the consumption function are for each period and all our grid points. And then we will loop backwards through t. If we're in the final period, then we will solve the last period problem, but otherwise we will construct an interpolator and we will solve the single period problem. So we will just sort of go backwards in time by doing this, and that will sort of gradually step back into our into the first period. And now I'm doing this for 8 periods, and in general you could do it for many periods, and you can do it sort of for each year in a life cycle, and then you will begin to have a life cycle model. But I will leave it up to you if you want to investigate that. Okay, so now we can plot our consumption function, and we can sort of see how they change over time, and we sort of analyze that in various ways if that's what we wanted to. This is mostly to say that this is a very general method that you can sort of apply to having many problems in a sequence. Okay, so now we have found policy functions. So that's saying, given what the state is in a specific period, what will your choice be? But you can also sort of ask us a slightly different question, which is that if we have some initial assets, we now want to know sort of a simulated path of cash in hand and consumption, where we draw random values of the idiosyncratic income. Okay, so how do we run such a simulation? What we do is we take our solution and then we construct a interpolation function for the consumption function in each period. So for each t here, we say, what if I wanted to interpolate from m to c? What should that function be? And I create a list of that. So I can define that. Then I can say, okay, let's say I wanted to have 10,000 individuals. Let's say I wanted to have knowing what cash in hand, income and consumption and assets are in each period for each individual. Then I need to start somewhere, so I simulate an initial distribution of assets. Here I just choose an exponential distribution that's somewhat arbitrary. And then I loop through time, where in the first period I start from the lagged assets, the initial assets. Otherwise I take the assets in the last period. I find what is the random value of consumption for each individual. I calculate what is the cash in hand. I apply my interpolated consumption function, and I calculate what is end of period assets. And this is just running the simulation in this way, and then I can sort of look at it in various ways. I can, for example, here I'm plotting what is the mean and the 25th and 75th percentile over time. So that's one thing I can investigate here. I can also sort of over time plot how does the distribution of assets looks to begin with in the initial period, or the -1 period. Then it's just the exponential distribution that I chose, but then sort of there will become sort of differences depending on which kind of income shocks you have received. So they will sort of, and eventually sort of people have having many different histories of shock, so the distribution will become sort of smooth again. Okay, for you here, I think it's good if you try to rerun this code, but with a higher n, so a higher number of consumers. That should luckily get things to be more smooth if you increase that. You can also look at, for example, the time profile of consumption instead of only the time profile of assets. That's also a good sort of task for you to work with. But otherwise, let me sort of begin to conclude here. So with these tools in this video, you can solve very complex models in terms of heterogeneity and uncertainty, and you can simulate the implied dynamics. And if you now begin to introduce various policies, it could be some sort of insurance policy or similar, then you can quantify their effects, not just on the average, but for the full distribution. For example, you can sort of have an idea for a life cycle model where you will add more periods to the stuff we have just done. You will make income time varying in terms of sort of both an income growth and retirement and so on. You can make income fluctuations persistent. You could introduce heterogeneity in preferences. You could introduce stochastic asset returns or heterogeneous asset returns, and you sort of begin to match this to data on household level income, consumption, and savings. And by doing this, you can sort of evaluate the effects of policies on inequality. So that's sort of showing the power of the tools that you're learning here. I should also say that what we have done here, it works theoretically much more generally. You can have multiple states. We only had one state, the cash in hand. You could have multiple choices instead of only consumption. There must also be a choice with respect to housing or respect to portfolios or similar stuff. And there can also be multiple shocks. So you can have shocks to, as I said, to returns and to income and so on. This is much more complicated stuff. You should not think too much about that. In this course, we have sort of master courses in the program for covering that. That was all for today. Thank you.